Hello, my name is Carlos Gabriel Reyes Morales, and in this video, I will present my individual analysis of the chemical and thermodynamic behavior involved in the functioning of automotive airbags, based on the work developed during the course. Airbags are safety systems designed to inflate extremely quickly during a collision. When a crash is detected, an iter initiates a rapid chemical reaction that produces nitrogen gas. This gas inflates the airbag in about 40 to 60 milliseconds, creating a protective cushion for the occupants. In this project, my work focused on analyzing the chemistry and thermodynamics behind the gas regeneration process. Inside the inflator, the gas is produced through three consecutive reactions. Step 1, sodium acid decomposition. This is the main source of nitrogen and produces reactive sodium metal. Step 2, reaction with potassium nitrate. This step consumes sodium and adds more nitrogen. Step 3, stabilization with silica. Combining all three steps yields to the global balance reaction, which is the foundation of all the stoichiometric and thermodynamic calculations. The next part of the analysis was to determine how much sodium acid will be required to produce the nitrogen volumes typically used in airbags. For this study, we assumed driver airbag will be 60 liters and passenger airbag will be 150 liters. Using the ideal gas law, PV equals nRT at 1.2 atmospheres and 300 Kelvin, the nitrogen required is driver 2.924 mole nitrogen, passenger 7.312 mole nitrogen. From the global reaction, every 10 moles of NaN3 produced 16 moles of nitrogen. Using this ratio, driver airbag requires 118.8 grams of NaN3, passenger airbags requires 297.1 grams of NaN3. These numbers reflect the theoretical mass of reactant needed to generate that required gas volume. We then analyzed the thermodynamic behavior of the global reaction. Based on the standard forming values, the reaction has these following results. A negative enthalpy indicates that the reaction is highly exothermic, which contributes to rapid gas expansion. A positive entropy reflects a large increase in disorder, since solids are converted into large amounts of gas. The combined effect gives a negative Gibbs of energy, meaning the reaction is spontaneous under the analyzed conditions. This table summarizes all the results: global reaction, thermodynamic parameters, required mass of sodium acid for each airbag, adjusted delta H, delta S, and delta G, and a brief interpretation identifying the reaction as exothermic, disorder increasing, and spontaneous. Although this chemistry is used to protect lives, sodium acid is highly toxic, and its products are corrosive. But proper disposal and recycle of airbag cleaners is essential to reduce environmental impact. Thank you for your watch.